In this video, I'm going to talk about something called vector-valued functions. In order to work with trajectories that are more realistic, in other words, trajectories that can be described in terms of 3 dimensions rather than just 2, I need to be able to define what happens when the trajectory changes over time across 3 dimensions. So let's imagine you're enjoying a barbecue on your deck on a nice warm day, and of course there's a mosquito present trying to get a snack as well. You're going to keep an eye on this mosquito and swat it when it lands. So here's my guy in an apron cooking at his barbecue, and here's a mosquito buzzing around. If I took a quick snapshot at this particular instant, I could put myself as the chef at the origin and the mosquito at a point in space. I can then construct a vector that goes from me to the mosquito. And this single snapshot will give me a single position vector that can be expressed as the vector r is equal to the components x, y, and z. But of course, the mosquito has already moved on. So now, if instead of a single photo, I take a quick burst of sequential photos of the mosquito over some period of time, now I'm going to have a series of these position vectors that are going to track where that mosquito is over that period of time t. So I'm going to be standing there, and I still serve as the origin of my vector and construct a vector to a mosquito that sits somewhere off to my left. Then I take another quick photo, but this time my mosquito is a little bit higher above the previous position and a little bit closer to me. Then I take another quick snapshot. This time my mosquito has risen higher in the vertical, but not too much closer to me. Then he's moved again. I take another quick snapshot, and then I take yet a 5th snapshot. Now the trajectory of the path my mosquito has taken can be given in terms of these components that change over time. If I construct a line that starts at the position of the mosquito and my first snapshot and connects to each position subsequent to that as the mosquito moves in time, I can describe a trajectory that is a vector whose components all depend on time as well. My vector r as a function of time is given by the components x of t, y of t, and z of t. And there are 2 ways that I can think about this model. The first is that it is a set of 3 parametric equations, x of t, y of t, and z of t, that describe the trajectory or curve in space. The second way of thinking about it is as a vector-valued function, where my vector has 3 dependent variables, x, y, and z, that are each components of the vector r, and each dependent variable or component of my vector varies with respect to the independent variable t, which in this particular case represents time. Both interpretations are good to keep in mind at the same time. I can have a vector-valued function, r of t, with components x of t, y of t, and z of t, all of which varies with the independent variable t, or I can vary t, and each coordinate x of t, y of t, and z of t on a parametric curve will also vary. A unique line in R3 can be determined by 2 distinct points in space, but I can also determine a unique line if I know one point and a direction. In either case, I need 2 pieces of information to construct a unique line, but this allows me to derive parametric equations for a line that exists in space. We're going to let L be the line that passes through some point p sub 0 defined by the coordinates x sub 0, y sub 0, and z sub 0. And this line is parallel to a non-zero vector given by v is equal to the components a, b, c, where p sub 0 and my vector v are already given. The fixed point p sub 0 is associated with a position vector r sub 0, which is equal to the vector O p sub 0, which is given by the components x sub 0, y sub 0, z sub 0. I'm going to let a second point, P, defined by the coordinates x, y, z, be a variable point on the line L, with the vector r equal to the vector OP, which is equal to the component vector x, y, z. This is a position vector that's associated with the point P in space. Now, since my line L and my vector V are parallel, the vector P sub 0 P is also going to be parallel to the vector V. This means that the vector P sub 0 P will be equal to some value T times the vector V, where T is a real number. And I can write this as the vector OP is equal to the vector OP sub naught plus the vector P sub naught P, which tells me that the vector OP is equal to the vector OP sub naught plus T times the vector V. But my vector OP is already specified as the component vector xyz, and my vector OP sub 0 is specified by the components x sub 0, y sub 0, z sub 0, and T times the vector V is just T times the components a, b, c. This can be written in compressed form as the vector r is equal to the vector r sub naught plus T times the vector V. Now, if I equate the components, I can also describe this line using parametric equations. X is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct, and this is for t ranging from negative infinity to infinity. The parameter t determines the location of the points on the line. At t is equal to 0, we're at p sub 0, and as t increases from 0, we move along the curve in the direction of the positive vector v. If t decreases from 0, we move along the curve in the direction of negative vector v. Note that t can vary over all the real numbers, and my vector r will sweep out the entire curve for my line L. If I don't happen to know the direction of vector v, but I know 2 points on my curve, say p naught and p sub 1, then the direction of the line will be in the direction of the vector p naught, p sub 1. This will be given by the components x sub 1 minus x sub 0, y sub 1 minus y sub 0, and z sub 1 minus z sub 0. An equation of a line passing through a point p sub 0 with coordinates x sub 0, y sub 0, z sub 0 in the direction of the vector v given by the components a, b, c will be given by the vector r is equal to the vector r sub 0 plus t times vector v. In component form, I get the components x, y, z is equal to the components x sub 0, y sub 0, z sub 0 plus t times the components a, b, c for all real numbers t. This in compressed form becomes the components x sub 0 plus at, y sub 0 plus bt, and z sub 0 plus ct for all real numbers t. Equivalently, the parametric equations for the line are given by these components. X is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct for all real numbers t. Now I want to work an example. I want to find the equation of a line that passes through the points 0, 4, 8 and 10, negative 5, negative 4. My vector v is going to be given by the components 10 minus 0, negative 5 minus 4, and negative 4 minus 8. This is just the vector 10, negative 9, negative 12. My vector r sub 0 is the vector from the origin to the first point. That's going to be given by the components 0, 4, 8. My vector r is specified by the vector r sub 0 plus t times the vector v. This gives me the vector r as a function of time is equal to the components 0, 4, 8 plus t times the components 10, negative 9, negative 12. This gives me the vector specified by the components 10t, 4 minus 9t, and 8 minus 12t. Here's another example. I want to find an equation of the line through the point 1, negative 3, 4 that is parallel to the line specified by the vector r of t is equal to the components 3 plus 4t, 5 minus t, and 7. Again, I'll use the equation that my vector r is equal to my vector r sub 0 plus t times the vector v. My vector r sub 0 is the vector from the origin to the point that I'm given. This gives me a vector with components 1, negative 3, and 4. In order for my line to be parallel to the given vector r of t, the slope of my line has to be equal to the first derivative of the vector r, so that my line has to be in the direction of components given by the coefficients of t. This means that my vector v is going to be equal to the components 4, negative 1, and 0. So my vector r of t is going to be equal to the components 1, negative 3, 4, plus t times the components 4, negative 1, 0. This gives me a vector specified by the components 1 plus 4t, negative 3 minus t, and 4. Here's another example. I want to find the equation of the line segment that is between the point 1, 0, 1 and the point 0, negative 3, 1. We are going to use the same approach here, but I have to be careful about restricting my values of t so that it gives me only that line segment. My vector v is going to be given by the components 0 minus 1, negative 3 minus 0, and 1 minus 1. This gives me the vector with the components negative 1, negative 3, and 0. I'm going to let the vector r sub 0 equal the vector from the origin to the first point. This gives me the components 1, 0, 1 for my r sub 0 vector. T times the vector v is going to give me the components negative t, negative 3t, and 0, so that my vector r of t is going to be given by the components 1 minus t, negative 3t, and 1. This equation is for all values of t, but remember, I only want this line segment piece. I'm going to look at t is equal to 0. This gives me the vector r at 0, which is specified by the components 1, 0, 1. At t is equal to 1, my vector r of 1 is given by the components 0, negative 3, 1. These are the two endpoints I'm looking for, so that my vector r of t is given by the components 1 minus t, negative 3t, and 1, provided t is greater than or equal to 0 and less than or equal to 1. So now you get to try it. Pause the video and find the equation of the line that passes through the point 1, 0, 1 and that is perpendicular to the two vector lines specified by r sub 1 of t is equal to 3 plus 2t, 3t, and negative 4t, and r sub 2 of t is equal to t, t, negative t. When you're ready, restart the video to check your understanding. In order to find the equation, I'm going to start by finding my vector r sub 0. This is going to be the vector from the origin of my system to the point 1, 0, 1. This gives me vector components of 1, 0, 1. We require the direction to be perpendicular to both r sub 1 and r sub 2. I need to find the cross product of the components 2, 3, negative 4, and 1, 1, negative 1 in order to guarantee that I have a perpendicular line, because a cross product is always perpendicular to the two vectors that I'm crossing. This gives me a determinant of a 3 by 3 matrix with the first row populated by I hat, j hat, k hat, the second row populated by 2, 3, negative 4, and the third row populated by 1, 1, negative 1. This gives me a vector specified by the components 1, negative 2, negative 1. My vector r of t is given by the components 1, 0, 1 plus t times the components 1, negative 2, negative 1, giving me my vector r of t is equal to the components 1 plus t, negative 2t, and 1 minus t. I can work with vector-valued functions either in terms of the vectors themselves, or I can work with them in terms of the components expressed as parametric functions. Let me know if you have any questions.